Hello. Happy Monday. Oh boy. Monday is always like this. It's like this hangover because intestine or human intestine is like 20 feet long. So all the vodka, because during the weekend, I drink more vodka than weekdays. So what happens is I feel this too much vodka inside of my 20 feet of GI tract, and it's disgusting. I feel like throwing up. It's kind of alcohol poisoning, I guess. It's horrible. I don't like this feeling. Okay, so we are doing partition function, and we find some need to step back a little because let me open the curtain up there. We found some need to step back and uh, do some what quotient function and remainder function. Okay, so we need to find some of their properties. Okay, so the initial motivation for partition function is that we try to find what I try to learn Bernoulli's number. Okay, Bernoulli's number, and to understand that I needed to learn Stirling's number, and to understand that I need to learn partition function, and I learned that there's no fixed form, closed form, no known closed form for partition function. So, okay, let's find it. That's why we are here. Okay, so um, and we realized that we gotta find formula for generally. We need to understand more about remainder function. It's this, okay? Remainder function, all right? N or quotient function first. NQ L, okay? It's the quotient when n is divided by L, okay? And similarly, N R L is when you after you divide n with L, what's the remainder? Okay, so that's what this stands for. Okay, very simple function. Now, what we are interested in is this: N Q L minus A is what? Okay. What is this? Bug. I get really annoyed when there's a bug. It's a flying insect. I get very, very annoyed. Especially when it's mosquito. How did that guy get in here? Yeah, we want to find formula for this. Now it has three variables. Okay, how about it? N Q L minus A is what? Okay, as A go from 0 to L. Okay, so we want to find some generic formula for that. Okay, I'm sorry, R. R. Okay, so yeah, that's what we're after. Okay, because we want to get rid of Q and R. Okay, we want to express in a more algebraic term. Okay, and we realized that when A is equal to 1, we realized as an example, well, when A is equal to, how about um, well, if you divide a number, typically L is less than N, right? I mean, you can divide 5 by 10. What is quotient? Okay, let's make some example, okay? So, NQ1 is always N, right? And NR1 is always 0, right? N divided by 1, yeah, quotient is N and remainder is 0, right? Now, how about uh, one divided by N? We are dealing with just positive integers, natural numbers, okay? So for simplicity, 1 divided by N, quotient is what? It could be 0 or 1, right? If N is equal to 1, quotient is 0, remainder is 0. But N is more than 1, so it's 1 or 0. N equal to when N equal to 1, when N is more than 1, okay? So and N R 1 R N is equal to, again, 0 when N is equal to 1. This is 1 R, okay? And 1 if N is more than 1, okay? Similarly, 2QN is equal to 0 when N is more than 2. Quotient is 1. Quotient is 2 when N is equal to 2. When quotient is 2 when N is equal to 1, right? We are seeing the pattern here, okay? So that's good. 2Rn is equal to, it's kind of symmetric, like anti-symmetric kind of. 0 when N is equal to, there it is again, okay. So I killed it. It's so distracting, this flying bug. So distracting, so annoying, so I had to kill it, okay? So it was very annoying, very distracting. No insects are welcome here, and also I don't like cats visiting my yard. Cats, stray cats, because they poop. Okay, they're no good. Moose, yeah, they're welcome. Yeah, they poop too, but moose, they're scarce of the value, so I love moose. Uh, we'll do it from bottom. When n is more than 2. Remainder is 2. Can remainder be 1 ever? I don't think so. You know, I'm getting very hungry now. I better eat something. I don't know what to eat. Pretzels maybe? Sure. Let me eat pretzels. Do you mind? Oh boy, I am getting way too hungry, so I eat pretzels. But I cannot drink, you know. I don't want to drink. It's disgusting. My system is so full of alcohol, so I don't want to drink. So I just have pretzels, okay? So I eat pretzels like this. We'll do this later, okay? First, just explore. Let's just explore this function. Quotient function, remainder function. I don't know if it's been done before. And we don't care because we like exploring the process itself, so we enjoy it. Even if it's rediscovery, hey, so what? We had fun, alright? So. Ah. CQN. Okay. Gosh, I'm really hungry. Oh, boy. Now it's starting to deviate from our pattern. How about remainder function? I guess it has to do the modulo arithmetic, I guess. So probably, I'm guessing it's already discovered by somebody. I don't know. I don't have time to learn those things. I just have to wing it. We'll do reminder later, okay? So. Yeah. Are you following me? 5 divided by big number like 6. A number bigger than n. 5. Yeah, the quotient is 0, right? Mm. I made a mistake. Oh boy. We know when n is equal to 1, this quotient function value is always equal to this, the other guy. I'm sorry, I switched by mistake, switched the index, didn't I? Index variable, I'm sorry. But it doesn't matter, okay? You can switch the index around, that's fine. N being number theory is favorite variable, so we don't need to L. We don't need N. Alright. So, I think that's enough for my pretzel snacking. Six when N is two. N is one. Oh yeah. I don't know. Maybe it has to do with prime number theories. I don't know. Oh well. We gotta learn how to do this. So it's kind of getting boring. You know, that's why I drink when I do mathematics or when I discuss whatever in here because it's really boring. All right. I think that's it. I think I'm beginning to see some pattern here. Beginning to see some pattern here. So, basically, it goes like this. It looks like we know when n is equal to one, this the head we call it head number. Okay, we just call this guy L. Head number. Why we don't call it H? Because the head number, tail number n. Okay. When the head number H is whatever, yeah, you have some. When this tail number n is equal to 1, the quotient function is always equal to the head number. Okay, 6. Alright? And whenever n, the tail number is, or we can call it base number of this function. Okay, if tail number is bigger than the head number, it's always zero. Okay, and how far does it go? It goes to a 6 divided by 2. Okay, from then it suddenly jumps to n is equal to 1. Okay, so that's the pattern. Okay, you see, 7 divided by 2. Okay, 7 divided by 2, 3.5, right? We don't care about fraction. We only care about the quotient. 7 divided by 2, quotient is 3. Okay, the integer part of that, 3.5. Get rid of 0.5, okay? Just discard it. Okay? So yeah, you start from 0, this n, right? I mean, quotient value, start from 0, 1, 2, 3, and it stops. And it always works like that. Okay? We're getting it now. Okay? I think we can come up with a generic function for quotient function, generic formula for quotient function. Okay, we'll do, because it looks like it's not that difficult in this case. Okay, so we found a pattern here. Okay, and probably it's very generic pattern. And how about this 654? How far does it go? We may have to work out some more examples. Okay, let's maybe do two more. Maybe. Okay, so we'll do two more. Okay. Mm. I think I kind of got it. It stops when 8 divided by 2, which is 4, right? It should be bigger than that. Okay, so this n here, I gotta use different pen because I'm starting to see the pattern. Okay, so this guy is bigger than 8 divided by 2. And also this guy is bigger, strictly bigger than 7 divided by 2. Just like here, okay? So these guys, they are less than 7 divided by 2. Here, oh, less or equal to. And here, strictly larger than 7 over 2. Here, uh, less or equal to 6 divided by 2. And here, you have strictly larger than 6 divided by 2. Okay, so that's the pattern. Okay, so we'll work out about two more examples, okay, just to make sure if this pattern is correct. We want this pattern to be general, not, true, not just true for first A numbers. Okay, we want it to be correct for every single number out there. So we're gonna find generic formula. Okay, so Yeah, I guess it's not quite complete. Our pattern analysis isn't quite complete, okay, because it's not jumping directly to 8, but it's going jumping to 4 and then it jumps to 8. So, and also we have another guy here. Uh, this case, probably 8 divided by 3, I think. 8 divided by 3. It's like 2 point something something, and it should be larger than that. And down here, you have yeah, it's good that we did some more example because I'm seeing some our pattern recognition isn't complete. Okay, so we have to keep working it out. Yeah, we are running out of space, so we're gonna have to switch out the board. All right. I think it's more difficult problem than I thought. Sorry. This is not an easy problem. I hoped it would be easy, but number theory in general is not that easy. Number theory, uh, like prime number, for example, right? Yeah, number theory isn't very easy field in mathematics. I mean, what field in mathematics is that easy, right? If you go deep enough. Yeah, n more than 8, right? We can write that as n more than 8 over 1. Just to make it look like the rest of these guys, right? 8 over 1, 8 over 2, 8 over 3, blah blah blah, right? So let's try to apply that. Are they more than 9 over 2? Yeah. How about that guy? 9 over 3? Yes. Ah, it works. This guy is bigger than 9 over 4, right? Yeah. 2 point blah blah blah, right? And 2 is bigger than 9 over 5, right? I'm sorry to be so lazy, but hey, it's Monday, okay? 9 over 5. Yeah, 1 point something. 2 is bigger. And how about 1? Is 1 bigger than 9 over 6? No. But we don't need formula for that, right? So yeah, but just to verify, yeah, it doesn't hold when n is equal to 1. But that's fine because we already have formula for that. It's always equal to the head number when tail number is equal to 1. Okay? So yeah, this is our working theory, okay? So let's do some more. 8 over 4. Oh, we have a problem. They're equal, they're not more, it's not more than. Oh well. Okay, we have bunch of number here, so let's see. Is this guy more than 6 over 3? Yes. Is 2 more than 6 over 4? Yes. How about this? Is this guy more than 5 over 2? Yes. Is this more than 5 over 3? Uh-huh. Is this guy more than 4 over 2? Yes. Is this guy more than 4 over 3? Yes. Is this guy more than 3 over 2? Yes. But in this instance, it stopped working, okay? So we may have to make more examples, unfortunately, okay? Because I think we are getting very close. My gut feeling is, but I do feel the need to explore this quotient function further. Okay, we gotta make some more examples. Okay, so all right, we are getting close, I think. Okay, so yeah, during the weekend I smoke a lot as well, so I don't wanna even smoke. Okay, so yeah, no cigarette break. No cigarette break. I don't want to smoke. I don't want to drink. Yeah. I just want to detox. Detox Monday. How about that? Yeah, I kind of erased that, but yeah, I'm gonna take a picture of this before I erase this. Okay, so I just keep on writing without talking because the whole point of taking a break is to give vocal rest. So okay. Let's take a break, okay? I'd rather take a break. It's kind of getting too hot. it's good to have some break. During the break, I can't remember this floor function. Yeah, that's compact way to express this so-called quotient function. Okay, so what is it? It's like this. Okay, I can't remember. N quotient R can be expressed as using the floor function. Okay, N divided by R, floor. Okay, like for example, 7 divided by 3 is what? 2.7 divided by 3 is equal to what? 7 over 3 floor of that is equal to what? 2 point what 333 dot, right? 2.3333 floor that that's just integer that is the yeah, ignore all the decimal part. Okay, so it's equal to 2. But I'm not satisfied with this function. Okay, this is more like to shorthand, shortcut. Okay, I don't like this function. Okay, so I want an exact algebraic expression without this cheating. Okay. Okay, so yeah, that's what we're doing. Okay, so and believe it or not, yeah, I've seen this flow function in those two mathematical journal articles about partition function. Okay, they use some of this. So some there we have something in common. Okay, so those academia, these professional mathematicians, they use this, and but we don't want to use this. Okay, so we are going in a very different direction because the direction they took failed. Okay, so yeah. And so the professors I emailed to, it's good that they are not contacting me because I don't want to get distracted because we are not done yet. So I'll just keep publishing on Wikipedia. Okay. No, it's better than that. So you've done until what? 3? Okay. Let's keep moving. Let's do when it's 10. Head number is 10. Okay, so 10. Q. N is equal to, and N is 0. I mean, it is 0 when N is more than 10. It's 1 when N is equal to 9, 8, 7, 6. Okay? As you can see, they are more than 5. Okay? See what I'm saying? And they are less than. I omitted one number. 10, right? Less or equal to 10 over 1. Okay. 2. This is n, okay? N is equal to. You have 5, 4. That's it, right? So, which is more than 10 divided by 3, less or equal to 10 divided by 2. Okay, I know it's difficult to see. I'll share it with you once I found this solution. Okay, so it's good to see when I guess it's like what 10 over 3 less than that. So you and then you have what 10 over 4, right? So what 2 and 3? No, because this formula is incorrect. Okay, what a disappointment. Actually, it is correct. It is correct. Yeah, this guy's like 2 point what 2.5, right? Yeah, 2.5 more than 3 is more than 2.5, and this one is what? There's no equality there. So, ah boy, 10 over 3 less or equal to and more than 10 over 5. Yeah, so this is incorrect because you have 2 here. Okay, so when this tail number n is equal to what is tail number? Yes, divider. Okay, when divider is equal to 2, this quotient function value is 5, and yeah, 2 is less than 3.333, but it's not bigger than 10 over 5. It's equal to 10 over 5. I think the way it works is at the very end, we should just give it this equal sign. Okay, then it will work. It's kind of exception. Okay, exception uh, for this number 2. And that's fine because number 2 is easy, right? Also, when it's number 1, right? You have what back up here. Okay, I'm sorry, spitting all over. Um, I the last example here you have 10, right? Quotient value 10, and it's let's just work it out. The example. Uh, I'm sorry, I made another mistake. This is supposed to be 4. Okay, this is supposed to be 5, 1. That's not incorrect. 1 is not bigger than 1.6 whatever, right? So yeah, this formula doesn't even hold. Okay. So what is 2? This is 1.6. Yeah, 1 is not a number between these two. Okay, so for 1, for the what are these numbers? Tail numbers n. Okay, dividers. When it's 1, this formula doesn't even work. So we already have an exception. Okay, why stop? Why not have just one more exception? I mean, what's the harm, right? It looks like that's what we have to do. Okay, so Okay. Oh boy. So potentially we found a function, the quotient function. Okay. Yeah. I'm wondering how many rows are there. Because we have another sequence. You see, 0, 1, 2, 3, 5. It's quotient sequence of quotients. Okay, so I'm wondering if there's generic formula for that quotient sequence. It's like Alice's Wonderland. I mean, rabbit hole. We went into rabbit hole, and it never ends. Just one whole, one this whole lead to another hole, into another hole. This network of relations, sequences. Yeah, you kind of want to get out of here, right? Yeah, I know. So do I. But hey, mathematicians, there are people who do mathematics for their living, right? Why not us? We are not doing it for a living. We're doing it as a hobby. So when I was come to a programmer, in my job line of work, I dealt with a lot of numbers and a lot of mathematics. So that's why when I'm at home, I didn't do mathematics because I'm like, oh, I'm tired of dealing with all these numbers as a computer programmer. But now that I'm a paper pusher, yeah, I kind of miss doing this. Okay, so it's a good hobby, something different from what I do for a living. So, um, yeah, that's good. Yeah, this is why I should never get a job as a mathematician, my mathematics professor, because then I'm not going to enjoy what I would do. I'm not going to enjoy mathematics, okay? Because it become a job, you know. Let me move that board right here so that I don't strain my neck too much. 'Cause I'm trying to find some pattern here. This quotient quotient sequence, okay? I guess we can talk about we can come up with a brand new notion of function, sequence function, okay? What is a sequence function? The output of this function is a sequence, okay? So we have it right here. What's the input? In this case, input is just 10, right? 10 as the dividend, okay, the numerator. All right. What is n? Well, n is just a divider. Just yeah, what denominator in a fraction in a division. Okay. And quotient is as we variate n, n goes from what one to infinity, right? Yeah. What are the all the possible quotients? Okay, that's the quotient sequence function. Okay. Yeah, sequence function, quotient sequence function. Okay, quotient it give us quotient sequence of quotients. Okay. Yeah. So yeah, don't forget this guy. Okay, and on top you have 10. Okay, so this quotient sequence is a finite sequence. Okay, and it always start from 0, and it was always end, end with this input value 10. Okay, the head number of this quotient function. Okay, so numerator. All right, the divide, not divider. Divider, divide. Okay, maybe they call it dividend. I don't know, but it's numerator, denominator. Okay, so q. Yeah, you can think of it this as like division. All right. Okay. Wow. It's interesting that we don't have 4 as the division. Okay, or we don't have 6, 7, 8, 9. We can think define a inverse. I mean, not inverse, but reverse or contra quotient function, contra quotient sequence function that made up with all the numbers that's omitted here. You go like 4, 6, 7, 8, 9. There will be the contra quotient sequence function. Okay, you give out all the numbers that's omitted from here. Okay. Yeah, when I was looking at all this Wikipedia or other website mathematics about number theory, yeah, I kind of got a taste of how they develop mathematics. That is number theories, number formulas theories, like Durfee square, whatever. Yeah, it's very educational experience. Okay, so I'm kind of getting the hang of it. So okay, so um, trying to look for some pattern here. Okay. I have got feeling that it may have to do with prime number. Okay, looks like it may have to do with some prime number stuff because we are dealing with multiplication and division. Uh, so it may not be solvable because prime number we don't have function for that, right? That's I wouldn't even, at least for now, I wouldn't even try to go after prime number function because yeah, I hope we can find partition function closed form without having to know the prime number closed form formula because that doesn't exist either. I mean, it is for now. There's no closed form formula for partition. I mean, prime number function. Okay, so I mean, at least until now, nobody knows. Okay, so there's no known fixed form formula for prime number. Okay, I mean that's what I remember. As far as I know, there's none. Okay, so maybe I should look it up. Okay, but I don't know even go there. Okay. Yeah, we made an observation, right? As you can see, there's this vacuum, this empty space. So it's between 5 and 10, because 5 is half of 10, right? So there, whereas there's no number between one half of the head number and head number. Between one half and the head number itself, is there's nothing. Okay, that's common observation, and it's something we noticed before. Okay. Hmm. So it looks like the number of rows here, the number of this finite quotient sequence, okay, um, number of rows, okay, we're gonna need some notation, okay, so how many rows are here, okay, we'll do it like this, um, L, Q, N, but absolute value right here, okay, so this is this quotient sequence, this is a number of absolute value of quotient sequence, okay, quotient sequence, QS, okay, L, N, okay, quotient sequence, okay, so whatever, okay, so um, here we have 1, 2, 3, 4, 5, 6, right, and it's as if 10 divided by 2, okay, quotient is what, 5, so it's 5 plus 1 is equal to 6, but so it's either 10 quotient 2 plus 1 or 10 quotient 2 plus 2. That's what I've seen, what I noticed back there, okay? When do you add 10, what, L quotient 2 plus 1 or 2? When do we add 1? When do we add 2? I don't know. I'm still looking, okay? Still looking for it. Maybe it's good time to take a break, okay? Because yeah, it's not odd number versus even number of the head number. It's not that. I because it's not. Maybe it's that. Okay, maybe we need to make some more examples. Okay, because we're not making any progress here. So okay, let's make some more examples. We have plenty of room. Okay, so yeah, yeah. After break. Okay, so it's kind of getting chilly. So Okay, I don't want to give you any misinformation, so um, let me see if there's closed form formula for prime number. Okay, I briefly looked at it. I don't think there is one, but just to make sure, there's some continuous function, like differentiable, whatever, very complex stuff, just like partition function, but closed form formula prime number. Yeah, it's unknown. Okay, so just what I thought, but that's fine. I don't think we need it here. I doubt it. I hope not. There's whole another word, prime number. Oh, that's whole another big, probably the biggest topic in number theory. Like Riemann, you have Riemann, all those famous people. So yeah, we're not gonna go there. Okay, so we don't have time. At least not this time around, because maybe one day, someday. Yeah, that's just too big. Uh, there's a Mountain Everest, whatever. Yeah, we're not quite ready for that. I don't think. I'm not. I don't know about you, but yeah, let's go ahead and do some leg work, okay? Because that's all we can do. We gotta just make more examples and just hope we would see some um, patterns. So 0, right? Yeah, we'll use some shorthand, okay? When we divide this guy with what, 11, dot dot 11, well, 11, 10, 9, 8, 7, 6, 5. No, not 5. Quotient is 2 when it's divided by 5, 4. That's it, right? Yeah. Quotient is 3 when it's divided by 3. That should be it. Quotient is quotient 4? No, there's no 4. Quotient is 5 when we divide by 2. Okay. And then quotient is 11 when we divide by 1. Okay. So okay. Let's just do one more, okay? 0. Quotient is 1 when we're dividing by 12, 11, 10, 9, 8, 7, right? Quotient is 2 when we divide by 6, 5. Quotient is 3 when we divide by 4. Quotient is 4 when we divide by 3. There's no 5. Quotient is 6 when we divide by 2. Quotient is 12 when we divide by 1. Okay. So, one hypothesis is that, let's look at here. We can divide this into 3 groups. Singleton, singleton, they are always there, but singleton, singleton, okay? We want to find the number of rows in the middle, okay? Here you have 1, 2, 3, 4, 5. 5 rows in the middle. Here you have 1, 2, 3, 4. You have 4 of them. Okay? Over there, we have 1, 2, 3, 4. 4 of them. Okay? Well, we do one more example. Now that, or 2 more. Now that we have some room. Okay? 13QN. You have 0, quotient 0, quotient 1, when it's divided by 13, blah, 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 blah. 13 divided by 16 is what, 6 something? Yeah, 6, so 7, okay? Quotient is 2 when we are dividing with 6, comma 5. Quotient is 3 when we divide by 4. Quotient is 4 when we divide by 3. The quotient is 6 when we divide by 2. Then we jump and we quotient is 13 when we divide by 1. Okay? So how many middle group rows? 1, 2, 3, 4, 5. Okay? We'll do one more. Or 2 more. Quotient is 0, quotient is 1 when we divide 14 with 14, blah 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 blah, all the way to 8. Right? And quotient is 2 when we divide by 7, 6, 5. Quotient is 3 when we divide by 4. Quotient is 4 when we divide by 3. And quotient is 7 when we divide by 2. Quotient 14 when we divide by 1. I think, so how many middle groups are there? 1, 2, 3, 4, 5. Let me go back there. I'm going to switch out this board, and we already have a lot of examples back there, okay? So let me find the pattern of this. We have brand new sequence here, okay? It's the middle group sequence. The size of the middle group sequence is a subsequence, okay? Subgroup of this sequence set, okay? Subset. Oh, it's getting hot. Okay, we use green. Okay, so here you have this middle group, there's none, right? And here you have one middle group. Here, one middle group. Here we have two of them, two rows. Two, three, 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 four. Okay? It goes like here we have 0, right? So 0, 1, 1, 2, 2, 3, 3, 3, 4, 4, 4, 5, 5, 5. So far. 0, 1, 1, 2, 2, 3, 3, 3, 4, 4, 4. Okay, so 0, there's 1, 0, 1, 1, 2 twos, 3 threes, 3 fours. Yeah, you gotta keep moving, okay? So, because this might have to do with prime number, okay? Because as we increase this head number, there will be more and more prime number getting added into. Okay, so we didn't want to invite this prime number, very unwelcome guest, because it's notoriously difficult problem. I mean, there's some prime number theorem, whatever, right? But we rather not deal with prime number at all, because we don't have to switch out the board, okay? So I'm not ready to erase anything, and we're running out of space, so. Yeah, it's Monday, okay, it's. I'm not depressed or anything, but Monday's not the best day of the week. Monday's difficult. Monday is not easy. Not easy day for me. Because during the weekend, yeah, I don't run during the weekend, so all I do is just drink, doing this. So it's a constructive way of spending weekend, because we are learning something new, discovering something new, teaching something new. But still, it's not very. After weekend, my body, yeah, just doesn't feel good. Okay, so. I'm gonna drink a little, okay? Because I think my body has detoxed quite a bit, so I guess I can drink a little, just a little. Ah, boy. Okay. I just merged the two different what dandelion drinks, because they are both dandelion flowers. Alright. Okay. Because it's just getting way too dry. Oh boy. We're discovering sequence after sequence after sequence. We're just defining new sequences as we go along. Okay. So. Maybe some of this were discussed in some mathematics exercise problem at the back of your number theory textbook, right? Who knows? Something small, right? But yeah, whatever. Oh boy. But I don't think it's too bad. Okay, it could be bad, but this sequence that we are dealing with. So we stopped at 14, right? Okay. Oof, I gotta get some Tums. This is like burning down my asparagus, man. Oh boy. Maybe I should drink something lighter, like wine. We can do that. Ah. Yeah, it's good. It's good. It's good. So, 15. 15 Q N. Alright, we have good notation here, okay? So it starts from 0, right? And 1, I mean, is it? Quotient is 1 when the divider is 15 dot 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 15 divided by 2, 7. If we divide by 7, no, so it should be bigger than 7. 8. And quotient is 2 when its divider is 7, 6, 5, no, not 5. Quotient is 3 when divided by 5. How about 4? How about 3? No. Quotient is 4, no. When divider is 3, quotient is 5. And when divider is 2, quotient is 7. Okay. Oh, my shoulder is sore. Now we have 15 and 1. Okay, so how many middle group are there? 1, 2, 3, 4, 5. Okay. So far we have 4 5s. I'm gonna write down the sequence. This kind of like the middle group sequence. Okay. We have 0, 1, 2, 2, 3, 3, 3, 4, 4, 4, and then 5, 5, 5, 5. This is where we are at, right there. Okay, so this is when n is equal to not n, L. Okay, our head number. We call it H. Okay, so H is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I messed it up somewhere. Oh, there are 2 ones. Just one more one. Sorry. One, two, three, four, 5, 6, 7, 8, 9, 11, 10, 11, 12. I messed it up again. Where did I mess up this time? Two twos. Oh, the two twos. It's quite exciting actually. It's coming in a brand new sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, we got it. Oh, now it's getting hot. You know, when things are not going your way, you're pushing something and it's not being pushed, then you're like, oh, I'm hot, you know, metaphysically and physically, okay? 16, Q, N. Do you see any pattern here? I don't. That's why we just keep making examples like this, okay? So 0, 1 divided by 16, all the way to 9. Okay, so 2 is quotient of 8, 16 divided by 8, or all the way to what? Well, 8, 7, 6. That's that. So 3 is quotient divided by when it's divided by 5. Okay, 4 is when 16 divided by 4, and 5. Well, yeah, 5 when divided by 3. 2, you have 8. Then you have 16 and 1, right? So middle group 1, 2, 3, 4, 5, 6. Okay, so finally we have 6. We can do. So you remember when we calculated like position vector, position number, and then velocity and acceleration? We are we're gonna borrow that concept. Okay, we'll count. We'll just group. Okay, we have 0, right? How many zeros are there? Yeah, only 1, right? How many ones are there? 2. How many twos are there? 2. How many threes are there? We are grouping things and counting them up so that we want to find some pattern. How many 4s are there? 3. How many 5s are there? 4. Okay. We are building a pyramid, kind of. Okay. Each time we have become more metaphysical, more abstract. Okay. To find some pattern. That's all. Okay. Because we did find something. We find recurrence relationship of that a function we can call it mountain function, or the restricted partition function, which is even more general than partition function itself. Okay, we are trying to find closed form formula, not recursive formula for the partition function. Okay, and we ran into this problem to solve that problem. Okay, so it's a solved problem. It's opening up another brand new world. Okay, it's rabbit hole. Okay, maze. Yeah, it's amazing. With sarcastic overtone. Yeah, mathematics amazing. So math is a maze. 0, right? 1 when it's divided by 17, all the way up to 17 divided by 2 is what? 8.5. So if you divide by 9, yeah, you give us what? 2. Yeah, 8, 7, 6, and 3. When we divide by 5, 4 when we divide by 4. We, and 5 when we divide by 3. 8 when we divide by 2. 2 times 8 is 16. So finally 17 we divide by 1. Okay, so 1, 2, 3, 4, 5, 6. Okay. Yeah, I'm guessing there should be at least 4 6s. Okay. We'll see. Next, 18, Q, and look at us. We're being very efficient uh, in terms of this expression, this notation. Okay. So 1 divided by 18 all the way up to 10, right? Then 2, right? When we divide it by 9, 8, 7, 3 when we divide by 6, 5, and 4 when we divide by 4, and 6 when we divide by 3, and 2, 9, and that's that. Okay, we don't have to write 0 or 1, okay, because we're not counting those things. Okay, so again, it's 6. I'll guess, yeah, probably there's one more 6, okay, because so this is number 16, number 17, number 18, 666. The mark of the devil, huh? Whatever, it's just a number. We probably have 1 or 2, probably one more, only one more 6, okay? Because that's a pattern, right? You probably go like 1, 2, 2, 3, 3, 4, 4. We are not sure, okay? That's why we're gonna have to make a lot of examples, okay? And we have plenty of room downstairs too, so, and I have plenty of time, okay? So yeah, I do have plenty of vodka, but I cannot drink very much because my esophagus is recovering from weekends, drink a lot of drinking. So yeah, but I can drink just a little, very little. Oh, it's getting way too hot. Oh, well. That's that. Okay, 6. As we predicted, okay? Now, 7, okay, so next probably will be 7, alright? So because we are beginning to see some pattern. It's getting way too hard. Oh boy. Oh. Yeah, this room is like cooking like 78 degrees. I guess vodka is kind of kicking in. Okay. Ten, 9, 8, 7, 6. Six times 6 is 18. Okay, so 2, 10. We have 1. We don't do 1. Okay, so 1, 2, 3, 1, 2, 3. There's 6 of them. Still? Still? Ah. No recognizable pattern yet. No recognizable pattern yet. Okay. 1, 2, 2, 3, 3. We would hope this will be 4, 4, but it's not. It's still 6. So we have 5 sixes. So again, we are not recognizing any pattern. Okay, so it could correspond to the number of prime numbers. It may have to we do with some number of prime numbers. Prime numbers under 20. Like prime number counting function, it may have to do with that. Okay, it's unfortunate development because we don't want to go there. Let's do a couple more, okay? So we have time, we have plenty of room. Too bad I don't have plenty of esophagus epithelial cells. Finally, we have 7. Okay. So now let's step back and let's see this transition. Let's mark all the prime numbers. Okay. because I'm not sure if this guy has to do with some density, because it may have to do with some density of prime numbers. Okay, so I wonder it jumps when a brand new prime number gets added. Just one speculation. Okay. I don't think so. We are adding a brand new prime number here, right? We're adding brand new prime number, so it jumped. Okay, we added another prime number, another prime number. It didn't quite jump instantly, but we add another prime number. I don't see any pattern. Okay, so fortunately, oh, I really don't see any correlation, some correlation, some relationship between numbers getting added and jump in this what hyper sequence numbers. No, I don't see any pattern. Okay, so well that's good because we don't want this to be related to prime numbers. We don't want that. Okay, we try to keep out the prime number, this unwelcome visitor, this mathematical giant. We don't want that. Okay, we don't want them as our guest. Prime number is just too much. Okay, so all right. Okay. Uh, do you see any pattern yet, though? I mean, we don't want to keep doing this, do you? Interesting thing though, we thought actually 21 divided by 2 is 10, right? But 7 plus 2, because we gotta add 2, right? Because we got rid of the top one and under one, this bottom one. So it's actually this, the, what? We have to name it, right? How do we do it? Quotient sequence. We just call it quotient sequence, okay? Quotient sequence, uh, the size of the quotient sequence, okay, is actually uh, this number plus 2, okay, because we cut off the top and bottom part. So 9 is quite surprising to me because I thought um, it should be always 21, this head number divided by 2, quotient of that, which is 10, okay? I thought it would be always like 10 plus 1 or 10 plus 2. Okay? But that's the example from the lower numbers. That's how it was. Okay? For example, for 7 is 5. So 7 divided by 2 is 3. Yeah, 3 plus 2. But here it actually is less than half of that. Okay, so yeah, that hypothetical was wrong. Sometimes it's 21, okay, so 9, okay, 9. We call it just this, okay? 21 quotient n, absolute value of that is 9, which is equal to what? 21 q 2, which is 10 minus 1. It's less than that actually. That is quite surprising. Okay, that is quite surprising. And I gotta think about this. Let's add these two guys. Okay, so for zero, you have 22, blah blah blah, and then you have 21 divided when it's one, so it's like 9 here. Okay, so I think the number of rows is kind of decreasing. I mean, relatively speaking, probably we are adding more and more prime numbers, prime factors. I think that's why the number is kind of relatively decreasing. What I mean is, okay, I'm gonna add another layer in this sequence of numbers. Okay, so we are just adding this guy, adding 2 to this guy. Okay, adding 2. I'm gonna write actually in between. Okay, we have 2, 3, 3, 4. I mean 5, 5. Yeah, it's nightmarish, right? Yeah. Mathematics. Yeah, I hope you don't have mathematical nightmare, man. Sorry, 4, 4, 5, 5, 5, 6, 6, 6, 7, 7, 7. I'm just adding 2. Okay, 8, 8, 8, 8, 8, 9. So 20 and 21. What I'm saying is this. I mean, compared to this head number, okay, our absolute value of this quotient sequence, uh, it used to be what? Half of this guy plus 1, half of this guy plus 2, okay? But now it's half of this guy minus 1, okay? So it's very decreasing, and I'm suspecting it has to do with this brand new prime factors that gets added on. That would be my guess. Okay, so because so we are doing inductive reasoning and deductive reasoning at the same time. What is inductive reasoning? It's legwork. We just make a lot of example and try to find some pattern. That's the inductive reasoning. Deductive reasoning. So inductive reasoning is more mechanical, laborious, manual, low level, like physical labor kind of. Deductive reasoning is more brain work. Okay, it's more metaphysical. Okay, and it's more difficult thing to do. So, but we rather do inductive logic because it's easier. It take more time. It take more legwork, but we failed. Okay, so let's do deduction. Okay, deductive reasoning. Let's see why this is the case. Okay, it's like you start with some premises, logic, mathematical logic, that kind of stuff. Okay, so Let's think about prime factorization, all right? Prime factorization. We are dealing with a problem that's by far more general than prime factorization, okay? But so we failed to solve this problem, okay? So let's take a step back and uh, deal with easier problem, okay? Prime factorization, okay? Uh, I guess we're gonna have to switch out the board. We have some empty space here, so let's call it factor function. Factor function, okay? What is a factor function? It's a number of different prime factorizations. Or how about this? It's kind of like partition function, okay? Probably it's a lot easier though, I think. 6. How many ways to express 6? 6 times 1, right? 3 times 2. And that's that. Okay? We call it, yeah, factor function f. Absolute value of that, so that's 2. How many ways are there to express number 6 in terms of numbers, whatever numbers? So it's kind of like partition function, kind of, in terms of multiplication, okay? I think this is easier problem than this, okay? How about F4? We'll just denote it as F4. We don't want to write parentheses, right? Can you read? It's too light, right? So why don't I use red? F 5 5 times 1 is 1. So any prime number, okay, yeah, is factor number is always 1. Because there's only one way to express it. Well, not really. Actually, this is also can be expressed as 6. So actually it's 3. Okay? 6 times 1, 3 times 2, okay? So actually this guy is... No, 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 we don't want to count that, right? Because 6 times 1, that's 6, okay? So, no, yeah. Okay, so... Yeah, I think we should do this first before we try to solve this guy. How about F1? Yeah, that's 1, right? F2? 2. Because they're prime numbers, right? F3? Yeah. How about F4? 4 times 1. 2 times 2 is also 2. But 4 is not a prime number though. So I think it's the one and only composite number whose factor number is equal to 2. Very unique number, I guess. How about F6? Well, F6 is as well. Kind of behaves like prime number, huh? Wait a minute. No, prime number is 1, right? Yes, yeah, I'm sorry. 5, how many ways to express 5? You said 1 times 5, 5 times 1, so I'm sorry. F there's yeah, F7, right? F8. How many ways are there? Uh, 8 1, right? Then you have 4 2, 2 4 4 2. They're the same. That's it, right? It's a very slow growing function, and of course it kind of fluctuates too. Whenever it meets the next prime number, it goes down to zero. Huh? It's kind of interesting function actually. I don't know anybody talked about this or discovered this factor function. Okay, factor sequence because its input is successive natural numbers, so that's why any sequence is a function. Okay, it's a natural function, natural number function, whose input is from 1 2 3 or 0 1 2 3 4 5. Okay. By the way, yeah, F0. What do you know what F0 is? How many ways can you express zero in terms of two non-negative integers? Multiplication thereof, if we include zero. I give you like 10 seconds because this is kind of interesting. It's infinity, okay? So like 0 times 1, 0 times 2, 0 times 3, there are infinite ways to express 0. If we decide to include 0 in the picture, this Indian guest, right? 0 was invented by Indians in India. Okay, so very interesting. Yeah, yeah, yeah. Indian philosophy, Indian mathematics, very, very interesting, exotic, philosophical, like 0 connected with the infinity. Okay, philosophical. Only in India. Okay, Indian music like zither, their percussion, oh, amazing. Makes me cry because it's so beautiful. Indian percussion, Indian music, their musical instruments, amazing. Yeah, I need some vocal rest, so we'll take a break, okay? So yeah, we are not quite going anywhere, but we are going somewhere. We are not going making any progress though to our original goal. But we are learning something new. We are exploring. We are having fun, and that's all that matters. Okay, so it's all good. We'll take a break. Okay. Okay, I guess it's good time to switch out the board, I guess. Oh, rabbit hole, right? Endless rabbit hole. Ugh. We are discovering sequence after sequence, function after function. We're not quite sure where we are going with all this. Okay? This, I don't know if I should erase this. I'm hesitating. I'm really hesitating to erase this. Okay, so because this is not easy thing to write down. Yeah, this guy's better thing to erase because I would rather not erase this guy, okay? Because this just is too big to erase, okay? So I would rather erase this guy. This guy, yeah, we can redo it. Shouldn't be difficult to redo it. Probably I wrote this down somewhere. We are discovering sequence after sequence, function after function, brand new, at least brand new to us. I mean, we are going somewhere and nowhere, right? We are going everywhere and nowhere. Okay. Blind leading the blind, right? And we are lost in the woods of number theory. We are lost in this metaphysical jungle of mathematics. We are lost. We're totally lost. Totally. There's no compass. There's no map in this jungle of mathematics. No, there's no such a thing. Nobody knows. There's no guidance. But good thing we have vodka, okay, so. Alright, so let's move on. Factor function, okay? Where f0 is infinity, right? But we're gonna exclude that because it's interesting notion. F of 0 is infinity. Very interesting, okay? But we'll just do easy stuff, okay? F1 is equal to 1, right? Well, we'll just do this. F instead is equal to F2 blah blah, but rather than that we'll just do it horizontally, okay? Let's say n start from 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20. Okay, that's what we're gonna do, okay? Then f of n is equal to 1 1 1 2 1 2 1 8 4 2 2 5 12 is equal to what? 12 1 right? 3 1 14 is what? 14, 1, 7, 2. So 2, 15. One more way to express 15, okay? Just 2, okay. 16. You have 16, and then you have 8 times 2, 4 times 4. That's it, right? 17, yeah, that's just 1. 19, I mean 18. 18 is what? 9 times 2, 6 times 3. That's it, right? So 3. 19, back to 1. 20. Well, 10 times 2, 5 times 4. So 3. It's a very slow growing function. It's not only slow growing, it goes up and down, up and down, up and down, okay? It has to do with prime number. Okay, so unfortunately, I have a feeling that this quotient function it has to do with prime number. Okay, I'm sorry. What a disappointment. Okay, what a disappointment. Because we didn't want to go there. I feel like this juggernaut, mathematical juggernaut, this big thing is coming at us, or we are going at it without realizing it. At least we are discovering something. We're defining something new. You know, factor function, okay? Maybe it's already there. I don't know. I didn't study too much number theory. No. So basically it's this. We'll circle prime number, okay? Whenever well, one is not regarded as prime number for whatever reason, right? But yeah, you can see one as prime number, doesn't matter. Prime number by definition is just, two different number. Yeah, you can see one as prime number, it doesn't matter, okay? So the factorization, we'll regard one as prime number, okay? Because our definition of prime number is there's only one way to express in terms of multiples, okay? What is 1? 1 times 1. Okay. What is 2? 2 times 1. What is 3? 3 times 1. There's no other way to express. So, our definition of prime number, okay, is when n belongs to this set of prime number is a Boolean function, Boolean equation definition, okay? So if this guy is true, then n belongs to p. This is a Boolean expression itself, right? Okay, that's our definition of this prime number set. Okay, so yeah, okay, yeah. What is Fn? Yeah, it's a factor function. Okay, so looks like we have to touch prime number theory. We didn't want to because it adds to our workload, but looks like we have to. Okay, maybe we discover something new in prime number theory. Okay, it's a big field. It's like big country, big land. Who are the residents? Anybody who studied prime number theory. Okay, we kind of became an unwilling immigrant or visitor or traveler to this metaphysical country or prime number theory land. Prime land. There's nobody in this airport who came to greet us. We just crashed the party, I guess. Yeah, so let's do it. Who knows? Maybe we'll make some contribution to prime number theory. Okay. I mean, if we can find some prime finite closed form for prime number formula, yeah, there we be like not Nobel Prize, not Pulitzer Prize, but Fields Medal, which is like Nobel Prize for mathematics. Yeah, sure, whatever. Yeah, it's possible. Okay. We have different point of view. Okay, at least we can contribute something. If not, we may find formula for prime numbers. Okay, it's possible. What's the prime number? Yeah, yeah. Let's take a shot at it, shall we? Because we are crazy, right? P I. Well, it looks like pi. Okay, it's just p nth is nth prime number. Okay, by definition. So, for example, p 1 is 1. First prime number. We'll start from 1. Okay. p2 is 2. p3 is 3. p4 is 5. Fourth prime number. Okay. p5 7. Okay. I don't even know what prime number theorem is. I guess once I knew, once I read about it, maybe I understood at least what they intend to mean. But I don't know too much about prime numbers, okay? Because my mathematics is very short, it's very shallow. Now, P6 is 11, okay? P7 for 13, okay? There's no known formula to no closed form to calculate this, okay? Because algorithmically, yeah, we can just what is two? Yeah, there's this systematic method, right? You have two and multiples of two, like 2, 4, 6, 8, 10, right? You just cross them out, and what's left is the prime number, okay? Yeah. I mean, except one, because every number is one's multiple. So maybe that's why they don't include one to be a prime number, but well, whatever. I don't think it will be too difficult to define prime number mathematically because it's like telescoping, right? Telescoping. Um, you have multiples of twos and then multiples of threes, multiples of fives, multiples of sevens, right? And then there's this density distribution, right? What I mean by that is you have multiples of two, like here, 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 here. Because mathematics and physics, they go both ways. Sometimes, most of times, development in mathematics help the development of physics. But sometimes, development in physics help development in mathematics. Goes both way, two-way street. Okay. So in South Korea, this Korean uh, philosophers back in what 1400s, 1500s, there's this academic debate between form and interrelationship between form and substance. Okay, form they call it ki, ki. Okay, substance they call it yi, like principle. Okay, ki is like also means energy in this Chinese character, but copium. Okay, but in this context, in this philosophical debate by Korean scholars, yeah, it's about substance versus form, and uh, these two scholars, uh, both of them share same have the same last name as mine. Okay, so one of them said, yeah, it's always this. Okay, we have principle, we have substance versus form, right? Form they changes, so it's more like physics. Okay, substance something that never changes is what mathematics. Okay, so yeah, one school, just Mr. I'm not gonna tell you his name because I don't want to reveal my last name with you. Okay, so this guy said it's always this way. Okay, it's always mathematics helping the physics. But there's another guy who said no, it goes both way. Okay, but they're both right. Why? Because it's most of times, 99% times, it's mathematics helping physics. But once in a while, physics do help mathematics. Okay, so yeah, you're right. Most of times, there's mathematics helping physics. But sometimes physics actually help mathematics too. Okay, so whatever. Okay, we are dealing with some density concept. Density. Okay. Because there's this what Poincare conjecture. This Russian guy uh, proved that, and he used some physics concept to prove this Poincare conjecture. It was fairly recent. Okay, maybe 30 years ago, 20 years ago. Okay, after he proved that, yeah, he got the Fields Medal, the Nobel Prize for mathematics, and then he retired at very early young age. Okay, probably in his 30s. I don't know. He used this concept of expansion, contraction, or energy conservation kind of stuff. Yeah, very physics concept. He used that to solve this purely mathematics Poincare conjecture, something like that. Okay, so I remember having read about it, even watching this documentary about it. Okay, so yeah, Russians are very good at mathematics. Okay, so they are very well disciplined people, probably due to harsh cold winter. Okay, I'm in Alaska. I'm very well disciplined too. Alaska used to be Russian territory. I didn't know. But back in the days, I thought America bought Alaska from Canada. That's what I thought. But no, they bought it from Russia. Okay, so Canada, it's a nice country, but somehow this true idiot, what, Prime Minister or President Justin Trudeau, punk ass, fucking moron. Is one of the stupidest idiot in the world. Gay marriage, all that shit. I think it's a lot worse than President Trump. Yeah, President Trump is an idiot too, but President Trudeau or Prime Minister Trudeau, I think he's a lot stupider than idiotic than President Trump. Okay, why are all these politicians so stupid? Why are all the stupidest people go to politics and become presidents, man? Okay, so we're gonna approach this prime number theory in terms of density. Okay, you have density. Okay, maybe we can solve this problem. Okay, so you have 3 and then 6. Yeah, we borrow physics concept. 3, 6, 12, 15, 18, right? So what's the number density here? Well, if we just do 1, multiples of 1, the density is 1, 1, 1, 1, 1, 1. Number density, okay? Density in terms of multiples of 2, that's like 1/2, right? That's the density. How about multiples of 3? So this like telescoping, this crossing out the algorithm to find this prime numbers. I learned it in when I was in high school in Korea, South Korea, because their mathematics education is very advanced in South Korea. Okay, so yeah, I learned this in high school when I was in Korea. So we'll try to take a shot at solving this problem. Okay, yeah, attempting to solve prime number function, okay? Because we're crazy, we're stupid, okay? And we're ambitious. Because this mathematical juggernaut or prime number theory, they came to us. Or maybe we ran into us. We try to avoid that shit, but oh well. We are here, so. Maybe we'll discover some recurrence relationship, which maybe could be rediscovery. We don't care. We just want to have fun. Okay? We just want to challenge the giant. Me, I'm challenging President Trump in the 2020 election. Why? It's something fun to do. Even though I never get there, in the debate stage with him, maybe there will be just no debate even. That's fine. Okay. Yeah, it's fun to even at least try. Okay. So yeah, I'm running for president. Okay. 2020. So. Okay, so density, okay? So we have density of 1 and density of 1 over 2, density of 1 over 3, and what's the next prime number? Density of 5, okay? Uh, 1 over 5, then density of 1 over 7, okay? So there are bound to be some this intersection between the density. Let's think about ruler, okay? You have a centimeter scale ruler, right? With 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters. And you have another ruler with inch scale, British scale. 1 inch, 2 inch, 3 inch, 4 inch, okay? But there is some intersection. Just two rulers scale exactly colliding, coinciding, right? Yeah. There will be the common multiple, okay? So we have this ruler with it ruler of 3, okay? This one scale, one unit of this ruler is 3, 3, 3, 3, so it's like 3, 6, 9, right? And then below that we have a ruler whose this unit is 2, 2, 4, 6, And the very first intersection would be, of course, zero. If you go one level lower, yeah, you have zero, right? Yeah, you start from zero, 0, 2, 4, 6, 8. Okay, that's the first ruler we have. I mean, second ruler we have, and the first ruler we have is the this gap of this ruler is just one, right? The third ruler we have is just one unit in this ruler is 3. So start from 0, 3, 6. Okay. So yeah, there's this first interaction between second ruler and third ruler is 6. It's 2 times 3. Okay. So because we want to come up with a brand new way to look at prime number. Okay. Let's do that. Okay. Yeah. Because it seems we have to solve this prime number, this closed form. Okay, here's problem that we are after. Okay, find the closed form formula for prime numbers. Okay, find a prime number formula. That's what we are after now. Okay, because looks like we have to solve this problem before we solve the partition function problem. Okay, we didn't want this, but looks like we have to. Okay, yeah, we are ambitious. We believe in God. We believe in miracle. We are crazy Christians, crazy religious zealots, religious fanatics. So yeah, Goliath. Not we are not Goliathans. We are Davidans. Okay, descendants of David. Okay, so metaphysically speaking. Okay, so yeah, we are not afraid of Goliath. Okay, so mathematical giants. We'll take a shot at this. We didn't want this, but looks like we have to. Okay, so it's pretty, very pretty coloring. So I'm gonna take a picture of this. Okay. So and we'll take a break. Okay, and we have 15 minutes left. We may as well just continue. Okay, because it got more glitz in there, prime number, rather than partition function. It's partition function, yes, also unknown. No formula is known there. I mean, fixed form. Prime number formula is also unknown, but it's a lot famous, more famous, and a lot bigger, more glorious, glamorous subject. So we didn't want to deal with this, but we have to because it seems it's necessary. We have to go through this first to get to partition function to find it. Okay, so it's kind of exciting. Okay, because if we find this formula, yeah, we may become very famous. Okay, so at least let's fantasize that we can do it. That's a good starting point, don't you think? It's glamour. At least take a shot at it. We may never get there, but let's at least even try, so that we can die one day without any regret. Because at least we tried, rather than not even trying. Okay, I take a picture of this and we take a break and we continue. Okay. 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 Take 5. by now you should know like what kind of personality I have, right? Like oh, give me a second. I'm just lonely, lone Alaskan wolf, right? Lone Alaskan wolf. Then I'm running for president, just like Don Quixote, challenging this castle. Or yeah, the character in that Franz Kafka, that castle. Well, land surveyor, right? Inspector. We are just surveying the land, inspecting the land of mathematics or politics. They would not let me in to the castle. Okay, Franz Kafka. Yes, I didn't read from cover to cover, but I know what it is about. Castle, because I did read some of that. Franz Kafka, smart guy. Metamorphosis, castle, trial. He touched very this human condition kind of subject. I like him. Okay, to read his novels is not that easy. It's kind of boring. Okay, but I like him. He was kind of underdog when he was alive. But later on, yeah, he published many books posthumously. His friends and families, I guess. So yeah, I'm like Don Quixote by Cervantes in Spain, challenging these big guys when I'm nobody. That's like David on Spirit of David, Shepherd David, challenging Goliath. Yeah, I'm challenging President Trump, 2020 election. I'm challenging this prime number function now. Yeah, because I like doing things outrageous. Maybe because I'm single, I'm bored, I'm loner. I don't have any girlfriend. I got nothing better to do, so I like fantasizing, dreaming, perennial dreamer, daydreamer. And what else is there to do in Alaska, man? As a single guy, if you have a girlfriend, you have family, yeah, you can go hiking, right? But me, I got nobody. So okay, so from now on we'll focus on prime number function, prime function. Okay, partition function we have to do this first, it seems, and then what factor function, and then we can do partition function. Looks like we have to climb this mountain first. That's what it seems. Okay. Uh, Again, we didn't want to deal with this prime function, but it seems we are forced to. Okay, and guess what? We are embracing it. Okay, yeah, more glory, more glamour. Sure, let's do it. Because we have different perspective. I think we are ready to tackle on this problem because we have our methods. Okay, so okay, we're gonna take a break. Okay, I mean, we continue. But time is running out, so all right, we'll just continue. Okay.